Hi class, this is Dr. Selby here, and unfortunately I forgot to record the 24-minute exam review meeting we had earlier. So now I'm just going back and recording it. Some key conversions that I will be using in these slides are moles to grams using molar mass, and we used those last time. Moles to moles using the coefficients in the balanced chemical equation. A new one from last time is a conversion between moles and liters using the molarity. And molarity, the definition of molarity happens to be on your equation sheet. And then because volumes typically measured are in milliliters and molarity is per liter, we'll do a lot of conversions between milliliters and liters. And this is just a metric conversion. Now, it looks differently on your equation sheet. It just gives you the prefix milli is 10 to the minus 3, which means multiply the base unit by 10 to the minus 3. So you might write it as 1 milliliter equals 10 to the minus 3 liters, but that means the same as 1,000 milliliters equals 1 liter. And from my experience in teaching for so many years, I think my students prefer it this way because they're not dealing with negative powers of 3, which is a little bit of extra work sometimes with your calculator. Here are some key formulas on your equation sheet. In this video, we'll use molarity, we'll use the pH conversions, and we'll use the dilution equation. In this first problem, this demonstrates how to use molarity as a conversion factor. And the question is, how many moles of sodium hydroxide are contained in 750 milliliters of a 5 molar sodium hydroxide solution? Because I'm using molarity as a conversion factor, I'm not identifying that as my given piece of information. My milliliters is my given piece of information. And then my needed unit is the moles of sodium hydroxide. So in order to use molarity as a conversion factor, we're going to have to convert our volume to liters. So that's the first step. And then once we have liters, we can use the molarity to get to moles. So this is just a two-step problem. So I'm going to start with my given, the 750 milliliters. According to my plan, I'm going to convert those milliliters into liters. Milliliters goes on the bottom so it cancels, and liters is on top. Now I have liters, and I want to go from liters to moles, and liters needs to go on the bottom and moles on top, and this is coming from the molarity. And looking at significant figures, both the 750 decimal point and 5.00 have three significant figures, so we'll round to three significant figures. In this next problem, I'm also going to use molarity as a conversion factor, but we're going to take it one more step. So this question says, how many grams of sodium chloride are present in 55 milliliters of a 2.10 molar solution of sodium chloride? And again, using molarity as a conversion factor, I present my given then is the milliliters, and then my needed is grams of sodium chloride. So first step is to convert milliliters to liters so we can actually use that molarity to go from liters to moles. So first step, milliliters to liters. Second step is liters to moles using molarity as a conversion factor. And then the last step is to use the molar mass of sodium chloride coming from the periodic table to convert to grams. So we're going to start with our given, the 55 milliliters. According to our plan, we're converting from milliliters into liters. Milliliters goes on the bottom, so it cancels. The next step is to convert liters into moles using the molarity. Liters goes on the bottom, so it cancels, and moles goes on top. Next step is to convert moles into grams, and that's using the molar mass of sodium chloride from the periodic table. Moles needs to go on the bottom and grams on top, so we're left with grams. And so I calculated that from the periodic table, and then we're going to round to the 55 has 3. This is exact. This has 3, and this has 4. We'll round to 3, and we get 6.75 grams of sodium chloride. In this problem, we're just going to calculate molarity. It says calculate the molarity of a sodium chloride solution made by dissolving 16.6 grams of sodium chloride in a total volume of 500 milliliters. So I'm given both grams and milliliters, and I need molarity. And what that means is I need to divide moles by liters. So first, I'm going to convert grams to moles using the molar mass. Then I'm going to convert milliliters to liters using the definition of milli. And then finally, I'll divide moles by liters. So here's the first step. We're taking our grams of sodium chloride. We want to convert it into moles. So the grams goes on bottom and moles on top. Because this is a multi-step problem, I want to hang on to a couple extra digits, and then just round to 3 sig figs in the end. For the next step, it's milliliters to liters. And then I'm just going to divide the moles by liters in this last step and round to 3 significant figures. In this next problem, we're going to have a dilutions problem. It says what volume in milliliters of 9 molar sulfuric acid is needed to make 6.5 liters of a 1.25 molar solution. We're looking for the volume of the concentrated solution, and we're given both volume and molarity of the diluted solution. On your equation sheet, you have this equation. I usually use M1V1 equals M2V2. Here, it doesn't matter if you call M1 the diluted solution or scenario 1 the diluted scenario or scenario 2 diluted scenario, just as long as that you have the information about what type of solution is on one side of the equation. So I will use this M1 V1 equals M2 V2. I need to define my variables, and I'm going to define my dilute solution as condition 2. So V2 is that 6.50 liters. My molarity 2 is the 1.25 molar. My molarity 1 is the concentrated solution, the 9 molar, and so I'm looking for V1, the volume of that concentrated solution. So I want to rearrange my equation for V1, and I do so by dividing both sides by M1. So now that we have V1 isolated, I just want to plug and chug my variables. And this will give me my volume in liters, but the question asks for milliliters, so we have to convert that to milliliters, and that's by multiplying by 1,000. Everything here, the 9.00 molar, 6.50 liters, and 1.25 molar has 3 significant figures, so I rounded to 3 significant figures. In this next problem, we're asked how many milliliters of a 0.755 molar sulfuric acid solution is needed to react with 55 milliliters of a 2.5 molar sodium hydroxide solution, and we're given the balanced chemical equation. What I like to do for these problems is write the pieces of information I'm given for each reactant. And for sodium hydroxide, we're given 55 milliliters and 2.5 molar. For sulfuric acid, we're given the molarity, and the volume in milliliters is the question mark. So we need to find milliliters. That's our need of the sulfuric acid solution. But some key strategies in these problems is we're going to use molarity as a conversion factor, which means we're never starting with the molarity. And then remember that in any chemical reaction, you'll need a mole to mole conversion using the coefficients in the balanced chemical equation. So that's going to be somewhere in the middle there. Okay, so as I said before, our needed unit is milliliters of that sulfuric acid solution, and we're given milliliters of the sodium hydroxide solution. Somewhere in the middle, I'm just putting it in the middle here, we'll need to do a moles of sodium hydroxide to moles of sulfuric acid using the coefficients in the balanced chemical equation. In order to get to moles of sodium hydroxide solution, using the molarity as a conversion factor, I need to convert milliliters of sodium hydroxide into liters, and then I can use the molarity to get to the moles of the sodium hydroxide. Then I'll just use the coefficients. Okay, so we're going to use the coefficients in the balanced chemical equation to convert between moles of sodium hydroxide and moles of sulfuric acid. Once we have moles of sulfuric acid, we can convert that to a volume in liters using the molarity. And then the last step is just to convert liters to milliliters using the definition of milli. Okay, so I believe I will do this all on the next page. There's my plan repeated. We start with our given, our milliliters of the sodium hydroxide is 55 milliliters. I'm going from milliliters into liters. Milliliters goes on the bottom, so it cancels, and liters on top. Then I want to convert, according to my plan, liters into moles using the molarity, and liters needs to go on the bottom, so it cancels, and moles on top. Now I want to go from moles of sodium hydroxide to moles of sulfuric acid. We want moles sodium hydroxide to cancel, so they go on the bottom. And moles of sulfuric acid will go on top. And this is coming from the coefficients in the balanced chemical equation. So 2 moles of sodium hydroxide is required to react with 1 mole of sulfuric acid. The next step is to convert moles of the sulfuric acid into liters of the sulfuric acid solution, and we're using the molarity. We need moles to go on the bottom, so it cancels, and liters on top. And then our final step is just converting liters into milliliters. Liters goes on the bottom, so it cancels, and milliliters on top. And then we'll punch this all in our calculator and round to 3 significant figures because 55, 2.5, 0.755 all have 3 significant figures. The conversion between milliliters and liters is exact. The coefficients here, this conversion here, these are exact, and that's exact. So we round to 3 significant figures, and we get 91.1 milliliters of that sulfuric acid solution. This problem asks us to label the acid and base reactants and the conjugate base and conjugate acid products. Some key points are that acids donate protons and bases accept them. And when an acid reactant loses H plus, the result is the conjugate base in the products. And when a base reactant gains H plus, the result is the conjugate acid in the products. So these go together with pairs, so I want to pair them up. And uh, it's obvious these uh, are different by a proton. And comparing the reactant to the product to get to the product ammonia, that NH4 plus or ammonium cation donates an H plus. Then we'll pair the H2O with the hydronium ion. They differ by a proton. And then comparing reactants and products, it's clear that the water reactant picks up H3O plus. And so it gains an H plus when you're comparing reactions to products. And then we can label our acid. Always going to be a reactant is the ammonium ion, and its conjugate base is ammonia. And then the water is acting as that base, and its conjugate acid is the hydronium ion. There are some extra problems in the exam review activities that go through more examples like this. Another skill is just identifying acid conjugate pairs by formula. I did make a micro lesson video on this and posted it in this week's announcements. Basically, if you're given any formula and you ask for a conjugate base, you're going to take away an H and you're going to reduce the charge by one. So for the formula of a conjugate base, you take away H plus. So just take away H atom and decrease the charge by one. And so doing that, we would get carbonate or CO3 with a -2 charge. For any time you're asked for a conjugate acid and you're given a formula, you're going to add an H atom and you're going to add one to the charge. So here we have one H, we would have two H's then. Here we have a -1 charge, we'd have an overall 0 charge in the end, and the answer is going to be H2CO3 or carbonic acid. Here in your exam review, I posted 4 different scenarios where you're going from one of these variables to all the other variables. So I'm just going through one scenario as an example problem. I also made a micro lesson video that illustrates how to use your calculator for this, and that was posted in the announcements this week. Note that we're going to express our pH and pOH to the hundredths place and use 2 significant figures for H plus or hydronium and hydroxide ion concentrations. These brackets mean unit molarity. Okay, so these are equations that are given on your final exam equation sheet. And for, I'm given pH and I can calculate pOH using this relationship. I'll use 14.00. And then so rearranging, we're just gonna subtract pH from both sides and we get pOH equals 14 minus pH, and that equals 9.50. I can go from pH to the hydronium ion concentration. Note that hydronium ion concentration and H plus concentration are used interchangeably. And to solve for this, it's H plus equals 10 to the minus pH, or that's 10 to the minus 4.50. Using your scientific calculator, that comes out to 3.2 times 10 to the minus 5 molar. Note when you enter answers on your exam, if you leave it like this, it'll be marked wrong. You actually have to enter in that value in proper scientific notation. So you have to use a calculator to figure what that is. And then similarly, I can take that pOH and get to the hydroxide ion concentration using this relationship. So my hydroxide ion concentration in molar is 10 to the minus pOH. That's 10 to the minus 9.50. Punch it in your calculator to get the actual value in correct scientific notation. And you get 3.2 times 10 to the minus 10 molar. That was the last slide. I hope this was useful. Thank you and have a great day.